We're going to study about electric field due to continuous charge distribution. Now, if you have any charge Q, then electric field is defined by electric force per unit test charge. And so electric field is given by a constant into the source charge divided by the distance from the source charge to the point we want to find out electric field into the R unit vector. So now we have to find out electric field due to continuous charge distribution. It is not a point charge anymore. So let us say that this is some arbitrarily shaped object and it has a total charge of plus Q. And now at a certain point we want to find out the electric field due to this charge distribution. Now this formula, which is the electric field, is given by this relation is valid only for point charges. And in order to use it for a continuous charge distribution, we shall divide this object into small parts or small volumes. Like in this case, I have already divided it into 3 volumes. Let us say that this small part of this object has a charge of delta Q1, and this small part of this object has a charge of delta Q2, and this small part has a charge of delta Q3. And let us say that we need to find out the electric field at a certain point P, the total electric field at point P due to whole of this object. So in order to find the total electric field, first let's say that we find out the electric field due to this charge and then this charge and then this charge. Now instead of drawing it here, let us say that the point P is somewhere here. Okay. Now these charges, they are so small that they can be considered as point charges. So now you know how to find out the electric field due to a source charge. Now this is the source charge and we need to draw R vector for this. So this will be your R vector for each of these point charges. Okay, so this R vector, let us say because of this point charge delta Q1, the R vector will be R1 vector. Due to charge Q2, it will be R2 vector, and due to charge Q3, it will be R3 vector. So because you know that electric field and R vector, they are in the same direction, and because it is a plus charge, so it will be a plus delta Q. So this electric field, let us say due to charge Q1, will be delta E1 vector. Due to charge Q2 will be delta E2 vector, and due to charge Q3 it will be delta E3 vector. Now what will be the direction of the unit vectors? Because you know that the unit vectors, they have the same direction as the vectors. So R1 unit vector, R2 unit vector, R3 unit vector, they will have the same direction as R1, R2 and R3. Now if we have to find out these electric fields, we can use this formula because it is valid for point charge, and these small charges, they could be considered as point charges. So let us find out what will be the value of delta E1. So from here we can say that delta E1 vector will be KE into source. What is the source charge for first one? So it will be delta Q1 divided by R1 squared R1 unit vector. Okay, please ignore this. And delta E2 vector will be equal to KE delta Q2 divided by R2 square into R2 unit vector. Similarly, delta E3 vector will be Ke delta Q3 divided by R3 square R3 unit vector, and so on. So if we have I number of these small parts, we can add all of them, and therefore total electric field will be approximately equal to delta E1 vector plus delta E2 vector plus delta E3 vector, and so on. So then the total electric field will be approximately equal to, let us put the values, and so it will be Ke delta Q1 upon R1 square R1 unit vector plus delta Q2 upon R2 square R2 unit vector, and so on. Okay, so we can also write it as Ke, and it is a summation of I number of parts, so it will be delta Qi Ri unit vector divided by Ri squared. So this will be the electric field approximately. Okay, but this electric field still is not completely equal to this. It's not completely equal to this relation. This is because these point charges, they are not exactly point charges. They are not infinitesimally small. So if we make them very, very small, then this entire area will be taken care of. So electric field will be equal to, take limit delta Qi tending to 0, so that this small volume, it becomes so small that when we add all of them, it becomes almost like a dot, and when we add all of them, it will take care of the whole of the area. Okay, so it will be Ke summation I delta Qi Ri unit vector upon Ri squared. Okay, so now if you have a limit of something and you are taking summation over the same, like summation over I, and it is a limit over delta Qi, then limit and summation, if they are joined together, it is equal to integral of that quantity. So it will be Ke can be taken outside, integral of delta Qi. So if it is an integral, it will turn out to be dq, and Ri will be R square into R unit vector. So this is a very common way of changing a summation into an integral, and we have done it many times in general physics 1 also. So when you have a limit which tends to 0 and it is on a summation on a certain quantity, then it can be changed into an integral. Okay, so if you have a continuous distribution of charge and you want to find out the electric field at a particular point, like in this case at a point P, then if you take an integral over the whole of the charge, you can find out the total electric field. Now based on this, you will have to solve some problems, but before solving problems you need to know a few more things, and like you should know what is volume charge density. So as the expression itself says, we need not remember anything. It is volume charge density. So it means it is density per unit volume of charge. Okay, and it is depicted by rho, and it is given by total charge upon total volume. So volume charge density means total charge per unit volume. Okay, In the similar manner, you can also have surface charge density. Surface charge density is given by sigma, and it is equal to total charge per unit area. Similarly, we'll have linear charge density. So it will be given by lambda is equal to total charge per unit length. Okay. So we'll use volume charge density if we have some volume and if there is charge distributed over this volume. It can be plus also and it can be minus also. Let us say, for example, we are taking this. If we have a volume and charge is distributed over the volume, we'll use volume charge density. If we have only a surface, a sheet of something, and charge is distributed over this sheet, then we'll use surface charge density. Okay. And if we have a line of charge, like infinitesimally small thin wire, so that will be an example of a linear charge distribution. So if you just have a thin line which it's just like a wire, it doesn't have a lot of thickness, we can approximate it to linear charge density. For linear charge density, we'll be using such a wire. Okay, so that's all for now.